All right, so we're going to move on and talk about chi-squared. So on the page after your graph and stuff, you're going to want to have a page where you set up for a chi-square analysis, as you can see here. You're going to rewrite your null hypothesis that we wrote before, and then you're going to want to copy the formula of chi-squared down on your note sheet. And then it would be helpful for you if you're not sure about the chi-squared definitions yet. So here are the definitions of these symbols. You have this big kind of E-shaped sign here, which actually means sum of. And then you have this O up here. O means observed. And then you have the E here, and E stands for expected. So pause here and write those down if you haven't already. All right, moving on. So basically, if I give you sample data, right, we have 3 sets of collected data. And say for, let me make this so that you guys can actually see what I'm writing. Say for sample data, we have round 1. At 10 minutes, we had, let's say 3 that were on the wet, and then that makes 7 on the dry. Remember, this is sample data, okay? And then in round 2, we had, let's say, for example, we also got 3 wet, 7 dry. And then lastly, on round 3, we had 4 wet and 6 dry. We're going to want to do an average of all of these. Now, for an average, that means that we're going to do wet, and then we're going to do an average for dry afterwards, okay? So that means for the wet, our average is going to be 3 plus 3 plus 4. And because we did 3 rounds, we're going to divide by 3. Okay, so that means we're going to have 9 plus 4 is 13 divided by 3, which equals, let me calculate that real quick. If you want to calculate on your phones too, that's fine, but I'm using my phone to record this right now, so it's kind of not an option. So that's 4.33. All right, so that's our average wet. Now we want to do, we're going to do dry, which means we're going to take 7 plus 7 plus 6. And again, we're going to divide it by 3 because we did 3 rounds. Now, we're going to do, that means 14, that means 20 divided by 3, which equals, it's going to be close to 7, but 20 divided by 3 equals 6.67. 6.67, and that's the average dry. Okay, so we're going to be using our nice big formula up here. And if you don't have space, you're going to go onto the next page like I am. But if you do have space, then you're going to try to keep it all on the same page because then it makes a little bit more sense. Okay, so using the formula, I'm going to rewrite it on the other side just so that we can keep track of it then. So again, the chi-squared formula equals the sum of the observed minus expected all squared over the expected. And this sum part is going to come in really, really important later. Okay, so we're looking for our chi-squared value. And our observed is going to be the average we just found. But our expected now is based on our null, right? Our null said that there was going to be no difference between the wet and the dry side, which means that our null, if it means no difference between wet and dry numbers, it would mean that we should have exactly 10 divided by 2 is dry, and then 10 divided by 2 is also wet. Now 10 divided by 2 equals 5, and 10 divided by 2 equals 5. So our observed dry and our observed wet should both be 5 mealworms. Okay, so this is what I have so far. If our null basically says no difference between wet and dry numbers, then each time we have 10, half of them should be on the dry side and half of them should be on the wet side. That's just what it means to have them not be different, right? Okay, so that means that we're going to do 1 for the dry, and then we're going to add the 1 for the wet. Okay, so if we're on the dry side, the data that we had was our observed for the dry side was 6.67. We're going to want to write 6.67 minus the expected, which is the, oh, sorry, this says observed, but this should be expected. Right, these are the expected values over here. We expected half, so we expected 5, right? So that should be 5. 6.67 minus 5, that's all squared, and then all over the expected, which is 5 again, right? And then we're going to be adding this big thing to the wet one, right? So in our wet one, the observed on this page, remember, was a 4.33. So we're going to write 4.33 minus, and our expected for the wet was also a 5. We're going to square that and then write our expected again, which is a 5 again. And then we're going to calculate both of these two, right? So to rewrite it linearly, especially if you're a math person, it should be 6.67 minus 5 squared over 5, and then added to 4.33 minus 5 squared all over 5. And that's going to give us a final number, right? So let me calculate this out for you for a quick second, and then I'll get back to the answer really quickly. Right, so it's going to be 6.67 minus 5. So 1.67 is going to get squared. And then that number is going to be divided by our expected, which was 5. That's going to end up being 0.55778. If it's a shorter number, you can write down the whole thing, but if it's a really, really long number, you can just round to the second or third decimal, okay? And then we're going to do the wet side now. Remember, this was the dry and this was the wet. If it helps you keep track, you can always write it down. Once you get practice with it though, you'll always work in the same order, so you'll be used to it. So we're going to do 4.33 minus 5. Right, and that's going to be negative 0.67. Now, negative 0.67 squared is equal to 0.4489, and then you're going to divide 0.4489 by 5, which is the denominator, which is going to be 0.08978. Now, that's kind of a small number, so that's kind of interesting. Now, you have these saying that you want to get them added together, right, to get your actual chi-squared value. So let's add those together now. So you're going to have 0.55778 plus 0.08978. And that's going to give you 0.64, and then we'll just round to the third digit. You can also just round to the second digit. I have no problems with either. Okay, so is this a big number? Not really, okay? and we're going to see what we're going to do with it really, really soon. So you have your chi-squared value from your data, and that is your 0.648. Now, the only reason this is important is because you're going to compare it to something. It by itself is not really important, okay? So if you go to the documents that I shared, there is an AP Biology equations and formula sheet. Now, on there, you'll find the chi-squared equation. This is the same exact formula sheet you're going to get on your exam. So you're not going to have to worry about memorizing this formula at all. They're going to be on your exam on the first page. So here's the chi-squared formula. And then you see this thing called the chi-squared table, degrees of freedom. Okay, that's important. Okay. The most important part is going to be this row that says 0.05. In biology, we always use a p-value of 0.05. So I'm going to write that down. But we're always going to use this row. Now, if you look across this row, there's multiple degrees of freedom. 1, 2, 3, 4, 5, 6, 7, 8. Technically, it goes on for a lot longer, but in bio, we'll never really hit more than 8. So you don't have to worry about that. So for degrees of freedom, you're going to have to figure out how to calculate that, right? So let me explain that in the simplest terms that I can. Degrees of freedom is going to be n minus 1. Okay, so let me go back to my page. Degrees of freedom equals n minus 1. Now, what is n minus 1, you might be asking? N is the number of treatments you have, right? How many environments did we have, right? We had 2 environments in our lab, right? We had wet and dry, right? So that means n is equal to 2. That also means that then our degrees of freedom in this lab equals 2 minus 1, which equals 1. Okay, so your p-value, your chi-squared value, and your degrees of freedom right now are all found, which means that we can use our table now to find our critical value. Okay, so I'm going to screen share again. And we're going to look at our critical value. So if your p is always going to be a 0.05, and your degrees of freedom in this lab is a 1, then where they intersect from 1 going down and from 0.05 going over is going to be at 3.84. So you're going to write down that your critical value is equal to 3.84. Okay, so I've written this down here, our critical value based on our degrees of freedom of 1 and based on our p-value of being 0.05, our critical value that we're going to be comparing to our chi-squared is going to be 3.84. Now, 3.84, is 3.84 greater than or less than 0.648? It's clearly bigger than, right? So if it's greater than, that means that the differences that we found from our data versus being evenly split between 5 and 5 isn't actually a big difference, right? So if we have a 0.648 and it's smaller than 3.84, then we're going to fail to reject our null hypothesis. On the other hand, if we had a number, if our chi-square was a big number and it was way bigger than 3.84, we would be able to reject. Okay, so we'll talk about that when that happens in another lab. But if you fail to reject, what does that even mean, right? Our null hypothesis, again, was saying that there is no difference between the wet and the dry numbers. And if we fail to reject it, it means that there was no difference. between our numbers of mealworms in the wet versus dry chambers, right? It's not a support versus not support thing. It's just that we were not able to show that the null hypothesis was incorrect in the case of our data, right? There was no difference between our numbers of mealworms in the wet versus the dry chambers because the difference from 5 and 5 was so small, right? 6.67 and 4.33 as our averages were not actually different enough from 5 to say that there was a difference, right? If you want to be really statistically correct, you would say there was no statistically, wow, spelling's hard. There was no statistically significant difference. Right here, there was no statistically significant difference between our numbers of mealworms in the wet versus dry chambers, right? That means that we were still close enough to 5.5 that we basically still had 5.5. Okay, if you did the lab a lot more times, you would get different results from your average. Maybe you get even closer to 5.5 if you did the results from your average, right? From a lot of trials. Now, if you are close to 5.5, that's fine. If you're not close to 5.5, that's fine too. But if you notice that they are pretty much evenly distributed between the wet and the dry, and there's no significant difference between the two of them, then is this really kinesis or is it taxis? Okay, let that be the question that you think about moving on from this.